Hello. Right. Um, Finishing off this cell fractionation. Again, we've done most of it. Right, so just to recap where we're up to: muscle tissue chopped into pieces, increase the surface area so that it's got high exposure for all the cells to this cold isotonic buffer solution. Why is it cold? Enzyme knowledge. Yeah, you can talk about enzymes. You'll do it on the other side of the course. Isotonic, good A level good A-level osmosis answer. Again, you'll learn it with me. Buffered, you just need to know that a buffer solution controls the pH. It's a chemical that resists pH change, and therefore the enzymes won't denature. Okay, so it's in the cold isotonic buffer, and then we've gone through why cold and isotonic is really important. Enzymes don't denature. No osmosis happens. Again, we'll be able to write better answers when we do it. The crucial thing is, I don't care if the cells burst. I care if the organelles burst or the organelles shrink. I want the organelles to be functional. Okay, so we do that, then we homogenize it, which means breaking the cells open in a gentle way to release the organelles in an undamaged form. Inevitably, the cells will break and they'll release their contents, but I've left behind like a broken open cell that's stuck to another broken open cell by collagen that glues the cells together. So there's going to be a lot of cell debris left over. Therefore, on the sheet it says, why do we filter it? Well, we filter it to have a sample of the organelles, but to remove cell debris. It's especially important with plant tissue because you'll hack through like a leaf because I want to work on chloroplasts or something, and you'll leave behind loads of cellulose cell walls. So I can filter off all that horrible cellulose, waxy cuticle, things like that, and therefore I just get my homogenate left. So after I've done homogenizing and filtering, I'm left here with a smooth homogenate. Okay, that is just basically the cell contents. There'll be a few fragments of membranes in there, but cell contents. Okay, so there's our homogenizer zipping around. The next thing we do on the sheet, it says that we transfer it into a centrifuge tube. You can notice that they are kind of like a bit pointy at the end because I'm going to want to, why's the pointer not working? There is. I'm going to want to kind of like get a small sample in the bottom, and it helps me to keep that separate from the fluid. So it goes to these small centrifuge tubes that goes into a centrifuge, a machine that spins. Yep, at hundreds of thousands of RPM. Revs per minute, revolutions per minute. Again, you might have been in a centrifuge at the fair where you're standing and it spins round. Anyway, centrifuges make heavy things move to the bottom. So we spin a centrifuge. So there's a little box that says centrifuge for the first time, and you need to know that when we centrifuge the first time, it's spun for a small amount of time at a relatively low speed. Okay, still like hundreds of thousands of RPM. It makes like a beep noise as it spins. It spins so at high speed. So yeah, low speed. So in that box, low speed, low time. Okay, when you do that, the biggest or most dense organelles get pushed to the bottom. So in the next box, it shows something like this, and it's labeled supernatant. That's the liquid part. And then the bottom bit is called the pellet or the sediment. That will contain the most dense organelle. That's nuclei. So there'll be thousands of nuclei all rammed to the bottom. Okay. If I'm doing forensics and I want DNA, that's how I'm going to get a pure sample of DNA from cells. Okay, so you need to know that the first one we get off is nuclei. Okay, all the rest are still floating in the supernatant. It didn't spin with enough centripetal force to push, the next biggest organelles to the bottom. Okay, so then we remove the supernatant. I go in with a little pipette. You come in. Where's my camera? There it is. I go in with a pipette and we suck out the liquid fraction and we leave the pellet behind. We don't spin it faster and keep it in the same tube because then you just get a layer of some more other organelles on top of those organelles. So you spin it once and then you remove the supernatant. You can pour it off sometimes, or it's better to just use a little pipette. Then, no shock, we spin it for longer and higher speed, and when we do that we get another pellet. So you see how the liquid's getting kind of like lighter. It started kind of very orange, it's got a bit less orange. Now the bit less orange has gotten almost yellowy. So that's the next fraction of the cells. So there's our supernatant, the liquid part. Then the bottom bit now, that's going to contain the next dense organelle, the mitochondria. Okay, and we can repeat it and repeat it, repeat it. The last organelle that we get out are the ribosomes. They're the smallest. And that's all we need to know. At the bottom of the sheet, it says, what's the order of sedimentation? Well, we need to know that the first, also, and it says in plant cells, the first thing we get are nuclei. That's number one. I find it hard with the camera. Number one, nuclei. If it's plant leaf cells, the next will be chloroplasts. They're a lot bigger than mitochondria. So chloroplast second, then you'd get mitochondria. Then we don't care. Yeah, it could be Golgi, RER, who knows? Crucially, the last thing we get off are ribosomes. Okay, and if I wanted to distinguish between bacterial ribosomes that are smaller than eukaryotic ribosomes, then I can do that with a centrifuge. In fact, the 70S for prokaryotic ribosomes and the 80S, the S kind of relates to where they would be separated out of in this process. So at the bottom of the the bottom of the sheet, in fact, you need to be saying that it goes from nuclei, chloroplasts, mitochondria, and the least dense, which is equivalent to smallest, are the ribosomes. Okay, and that's it for centrifugation. Okay, it's a nice and short one, but I said I'd send this, so there we go, done it.